So let's take a look at factor analysis. Here we have our data points x and our latent space z. We define a latent distribution as a standard normal Gaussian, and our transformation for generating a data point from a latent sample is a linear transformation with a weight matrix W and a bias mu. The mapping also has some additive noise, where each data dimension gets its own variance variable. Now we want to train a factor analysis model. To train a model, we can use the likelihood. Here the likelihood can be expressed as the marginal over all latent variables. Since we have a Gaussian distribution as the latent distribution, and we have a linear transformation, the resulting data distribution stays a Gaussian with the following parameters. The mean of the distribution is the bias of our generative transformation, and the covariance matrix consists of the weight matrix W times W transposed, plus the individual noise variance for each data dimension. For evaluating the likelihood, we do not only need the mean on covariance matrix, but at some point we also need to compute the inverse of this matrix, and we need to evaluate its determinant. Because we do the split of the covariance matrix to W and W transpose, we can rewrite the inverse and the determinant of the covariance matrix in the following ways. Both equations have a complexity which is cubic in a number of latent dimensions, and most of the time the number of latent dimensions is much lower than the number of data dimensions. Let's look at another algorithm which is called Probabilistic Principal Component Analysis. Again, the latent distribution is Gaussian, and the transformation is defined by a linear transformation with additive noise. So far this looks very similar to factor analysis, but the only difference is that the version has a single scalar representing the additive noise. Also, we have a constraint to keep the matrix W orthonormal. This algorithm now suddenly has a closed form solution for finding the weight matrix W. This boils down to an eigenvalue decomposition. You first need to compute the covariance matrix of the dataset and decompose it into the eigenvectors L and the eigenvalues lambda. You can then compute the weight matrix by using equation 11. Here we have a comparison between factor analysis and probabilistic PCA. Each picture is a sample from the generative model that was trained on pictures of the digit 7. We can clearly see the difference between the two algorithms by looking at how the additive noise is handled. In factor analysis, we have individual variances for each data dimension, while in PPCA, we have a single value as the variance. On the left side, we see that the background looks very clean, while the digit is very noisy, while the PPCA results on the right show that the same noise level is used for all pixels. Here we have the common algorithm Principal Component Analysis. This algorithm is closely related to PPCA. It holds in the case when the variance in PPCA goes towards 0. The idea behind it is to find a low-dimensional projection where the reconstruction error is minimal. We can also define a problem as maximizing the projected variance. Let's look at an example. The data points are shown as red dots. The violet line shows the plane where projections have the smallest reconstruction error. This reconstruction error is the combined length of all the blue lines. If we would rotate the violet line, these distances will increase and we would get a worse reconstruction cost. The solution for PCA is very similar to the one from PPCA. Here the weights matrix is directly composed of the eigenvectors of the covariance matrix of the data. But we still have a problem. How small do we want the latent space to be? Here we have an example for the first 4 eigenvectors of the covariance matrix of the digit 3. The eigenvectors are sorted by their eigenvalues with the highest eigenvalue on the left. The eigenvectors for the higher eigenvalues show high-level features, while the ones with lower eigenvalues show low-level features like local edges. This plot shows the sorted eigenvalues for such a dataset. As you can see, the values drop very fast. That means that most of the lower-level eigenvectors lose their significance very quickly. We can therefore decide the size of the latent space with these kind of plots by cutting off the eigenvectors at a certain threshold. Here's also another example for a phase dataset. This plot shows the eigenvectors of the covariance matrix of pictures of faces. They are again ordered by their eigenvalues. So on the top left you see very high level features like whole blurred faces. As the eigenvalues get smaller and smaller, you can see only local features like edges. A lot of these low level features can be discarded to reduce the size of the latent space. We can use PCA also as a preprocessing step, by using the weight matrix to transform the centered data into the latent space, and then scaling them with the square root of the eigenvalues. The resulting Z values then have an identity covariance matrix. In case of zero component analysis, we want to stay in the original domain, and we want the resulting data points as close as possible to the real data points. We are still scaling the features with the eigenvalues, but we transform them back into the data domain. Let's take a look at another algorithm which is called independent component analysis. The generative model is again a linear transformation, but this time there's no additive noise. All the noise is coming from the latent state and is then transformed into the observed space X. This again looks very similar to vector analysis, but the important thing here is that the latent distribution is not Gaussian. But how does the density look like? We can evaluate it by using the change of variable theorem, where we transform the observed data point into the latent space. Then we evaluate the density in the latent space, and we correct any deformations of the distribution with the determinant of the matrix transformation. That means that we are applying the inverse of the generative transformation, and then we try to shape this resulting latent state to fit the latent distribution. We can use these insights to train the model using maximum likelihood estimation. We can decide for different latent distributions, but the two major cases are the derivative of the sigmoid and of the tan H function. This then results in the likelihood shown here. This method will not result in a closed form solution, so we just train it by gradient descent. In the bottom you can see the gradient for the weight matrix W. So we learned how to train independent component analysis, where we use a linear transformation. But we could actually make this transformation more complex, for example by using a deep neural network. But computing the determinant of the Jacobian of this deep neural network will get intractable very fast. But there's one example, and it's called nonlinear independent component estimation, where we have a deep neural network, but this neural network has a special structure where the Jacobian is very easy to compute. In the next lecture, we will see algorithms which have the same benefits like the algorithms shown here, which feature deep neural networks, but it don't require the special structure like a nonlinear independent component estimation.